Okay, so we've talked about binding energy. Just to go back to Einstein's equation, E equals mc squared. What we can say now then is that we know that, we've already said this earlier, that you've got these four nucleons, separate nucleons, here they are, 2 protons, 2 neutrons, okay? And when we put them together and make a nucleus, and again, remember that's simplistic, you don't really just put nucleons together, it's not as simple as that. But, you know, if you just put them together and they form a nucleus, here they are, okay, those 4 nucleons, and that's now our helium nucleus. We know that when we do that, energy is released, okay? And the energy that is released is 4.54 times 10 to the minus 12 joules. Okay, sorry about the small writing there. All right, now, so what we're saying here is that that we know that the mass of this is less than the mass of this. Now that mass hasn't disappeared, it's just become energy. Okay, so the total mass and energy here is equal to the total mass and energy here. It's not like, as we said, these have greater mass. These individual nucleons have greater mass than the combined helium nucleus, but that mass hasn't just disappeared; it's converted into energy, and that is that basically is summarised by Einstein's equation here: E equals mc squared. So what we can say from this then is this: we can redefine conservation of energy slightly. Okay. Now we know conservation of energy is energy cannot be lost or gained, only transferred from one form to another. Okay, so energy can't be created or destroyed, is another way of putting it, only transferred from one form to another. It can't just disappear, or it can't just be created. Okay, but we could perhaps redefine this as conservation of mass energy, because it looks here like some energy is just being created out of nowhere, but it hasn't. It's come from the mass of these nucleons as they've been put into the helium nucleus. Remember, they're moving to a lower potential energy. This has got a higher potential energy than here. Okay, so that potential energy that's been lost as these things have been bound together and held together by the strong force, as the strong force has pulled these 4 things together, okay, they've moved into a lower energy state, they've lost potential energy, and that energy is released, okay? And that energy there is the binding energy of the nucleus, all right? It's the energy that is released when the nucleons bind together, or it's the energy that you have to put in to pull the nucleons back apart into their original individual nucleon state, so to speak, okay? So what we're saying here is energy and mass are sort of interchangeable according to Einstein's theory of special relativity, okay? And we can measure the energy in a body by multiplying its mass by c squared. So conservation of energy, we can just say, rather than just conservation of energy, conservation of mass energy, because mass and energy are interchangeable, okay? So it's important to be aware of that idea.